So in this video, we're going to talk about the mechanism behind aspirin poisoning. So uh, aspirin. There's different forms and doses of the drug. Like so, right? There's low dose aspirin for blood clotting, and then you have regular aspirin. So let's talk about what happens if you take too much aspirin. So here I have a schematic diagram of the electron transport chain. All right, here's my intermembrane space. Here's my inner membrane space, where the complexes or the electron transport chain is located, so etc, and then I have the matrix. So we have these various complexes, and as you've already learned that in complex 1, taking uh, the electrons from NADH, we essentially push approximately 4 hydrogens, H plus ions, into the intermembrane space. uh, we have coenzyme Q that takes the electrons, all right, that takes the electrons from complex 1 to complex 2, and in this case we actually use succinate in complex 2, and we're not going to go over the details, but essentially we oxidize succinate and reduce coenzyme Q uh, to get the electrons. So electrons again are transferred to coenzyme Q. Now, complex 3, we also have a gain of 4H plus or 4 hydrogen ions into the intermembrane space, right? As electrons is being pushed down the chain. Now, from complex 3 to complex 4, we actually use cytochrome. So we actually use cytochrome C as the electron carrier. Now, in the last part, in complex 4, we actually reduce oxygen to water and oxidize cytochrome C. In this process, we actually push approximately 2 hydrogens in intermembrane space, right? So the the details of the electron transport chain in this case is not important. What I'm pointing out to you is that in the intermembrane space, in the intermembrane space where these hydrogens are pushed, I have an abundance of hydrogens, H plus ions. And so this proton gradient is actually what we use to actually synthesize ATP with respect to the phosphorylation of ADP to ATP. So complex 5, also called ATP synthase, we have a channel that brings the hydrogen back through the F0 subunit, eventually to the F1 subunit where ATP synthesis takes place. So these hydrogens on the intermembrane side are going to eventually go down all the way down here to eventually enter the F0 space to go to the F1 complex. And that's how we create energy, right? That's how we create ATP. Now, aspirin, right, we could actually take salicylic acid, add acetic anhydride, and we get aspirin and acetic acid as a byproduct. So interestingly, aspirin, the structure looks something like this. And so the structure of aspirin looks something like this. So this is a double bond. Right? So the structure of aspirin looks something like this. And so we term aspirin as an uncoupler of the electron transport chain. So complex 5 I've put in blue here because it's kind of different from what we term the electron transport chain. So electron transport chain consists of complexes 1, 2, 3, and 4. Complex 5, it's kind of by itself as synthesizing ATP. So we say complex 5 is coupled to complexes 1, 2, 3, and 4. So what happens with aspirin is that if you get too much, it acts as an uncoupler of the electron transport chain. So what happens is that these negative charges actually come and they protonate or oxygen. And so what occurs as a result? So what occurs as a result? We create, even though it's slightly polar, it is enough to actually diffuse through the hydrophobic, and these inside the inner membrane is hydrophobic, but it becomes hydrophobic enough to diffuse across the inner membrane back to the mitochondrial matrix. So in other words, instead of using the H plus that we've created from the electron transport chain with the electrons losing the energies to create the protons, instead of them going to ATP synthase to create energy, we have this massive buildup of aspirin, which is taking away those protons and they're moving it to the mitochondrial matrix. As a result, we're not creating ATP. So in other words, the uh, ATP synthesis gets decreased significantly, right? So, and that is really bad. So ATP synthesis gets decreased significantly, and as a result, we've uncoupled the proton gradient. So instead of them going to ATP synthase, they're actually diffusing across the membrane. And so we term these sort of compounds uncouplers. Another one that acts similar to aspirin is 2,4-DMP, and the mechanism is pretty much the same. So if you're in an organic chemistry lab or something like that, be careful working with 2DMP, 2,4-DMP. But if you're a patient and you're taking aspirin, this is why uh, it's recommended to be very careful in terms of your dosage.